Alright, let's tackle lesson 4, which will discuss harmonic motion, and we're going to introduce our very last force model, and this is going to be with a spring. We've already covered friction, we've already covered viscous forces, so that was Coulomb friction and then viscous friction, and now we're going to deal with spring forces. We're going to follow tutorial 2.3 from the book, at least in the setup, and then I'll introduce to you the spring model, which is a little bit different than what you see in the book. And of course the whole point of having these, what I would say, more thorough models is that they can be more general. And so you'll see this is going to come in really handy once we get out of one-dimensional or straight line motion. So what we've got, sketch our system, step number 1. Is we have a spring attached to a wall that's then attached to our block. Our block has a mass m, and then this spring has a spring constant k, and it also has an unstretched length L0. So we've sketched our diagram. We need to put our reference frame on our paper. So this will be our reference frame I. We have an origin O. And then define our coordinates, where our coordinates will define as the position away from the wall be x sub m, and then don't forget gravity. Gravity is pointed down. So there's our system sketch, and then now we need to draw a free body diagram. And so for the free body diagram, FBD, we'll have our block, we have the force due to gravity, which is mg pointing down. We have a constraint force that keeps us from going through the ground. And now we need to deal with this spring force. Now here's the model that we're going to use for a spring force. And like I said, it oftentimes gets confusing about which direction to draw the forces. Now in the past, with our friction and with our viscous friction, I've said you always need to draw the force in this particular direction. So in this case, always draw the force in the direction that goes from the attachment point, which is on the wall, to the mass. And that's always the case. So we're going to draw this from pointing from the attachment point to the mass. Remember, it doesn't matter what side it's on. We'll call this Fs. And we're going to define this spring force F sub s as negative k multiplied times L minus L naught. And this is where L is defined as the distance from the attachment point to the mass. And where L naught is defined as the unstretched length of the spring. Okay. Alright, so we've got everything that we need. Your spring constant is going to be defined in the problem, as well as your unstretched length. Alright, so now that we have our free body diagram, we can then apply Newton's second law. And so Newton's second law tells us that our force in the x direction is equal to the mass multiplied times x double dot of your mass. And so the only force that we have is our spring force, and our spring force is negative K L minus L0 is equal to M x double dot M. And so our length L is the distance we said is the distance from the attachment point to the mass. And we've defined that in our diagram as x sub m. So here L is equal to x sub m. So we say minus K x sub m. And then L naught, actually defined in the problem, looks like I got this wrong. L naught, the unstretched length, was defined in the problem as x naught. So we'll say that L is x sub m minus x naught is equal to m x double dot sub m. And so then our equation of motion is now x double dot sub m is equal to negative K x sub m minus x naught, all divided by the mass. So there's our equation of motion. All right, it's time to solve. So for this problem, we're going to make a substitution that's going to make our life tremendously easier. In the book, they go both ways. So you can solve simply by doing a separation of variables, because if we start here with our equation of motion, x double dot sub m is equal to negative K of x sub m minus x naught divided by m. You can separate your variables, work through that, determine your constants, and then solve using trigonometric integration. However, the substitution we're going to make is going to really help out quite a bit. So what we're going to do is we're going to define a new variable. And so this variable is going to be a change in coordinates. We're going to define z is equal to x sub m minus x naught. You can already see how that's going to make our life a lot easier. We're taking what's a variable and a constant and just replacing that with a single variable. And then that means that if we differentiate this, z dot is going to be equal to x dot m minus x naught dot, right? So if we differentiate both of those, we know that x naught is a constant, so that makes this 0, and so z dot is equal to x dot m. And then if we differentiate that one more time, z double dot is equal to x double dot m. So that's our first substitution. Our second substitution is to take this k over m and make a substitution there. We're going to say omega naught is equal to k divided by m, the square root of that quantity. This is called the natural frequency. So this is one of these times where it's a substitution that we know where it's going, so we can make it and then make our lives easier. So if we substitute omega naught into our equation and z double dot into our equation of motion, z double dot is equal to x double dot m. So z double dot is equal to negative k over m xm minus x naught, which is the same thing as negative omega naught squared z. So now we have the differential equation z double dot is equal to negative omega naught squared z to solve, which is just a lot prettier than what we had earlier. So what we need to do is we need to assume a solution. And so we're going to assume the form that's z as a function of t is equal to A cosine omega naught t plus B sine omega naught t, which means that z dot will be negative A omega naught sine omega naught t plus B omega naught cosine omega naught t, and then z double dot will be the differentiation of z dot, in which we get negative A omega naught squared cosine omega naught t minus B omega naught squared sine omega naught t. And so we have our three forms. We've got our z dot, and our z double dot. And we need to plug this in. We need to plug these guys in back into our equation to see if this actually works. So check to see if the solution is correct. So we'll substitute this in. And so when we do our substitution, we get negative A omega naught squared cosine omega naught t minus B omega naught squared sine omega naught t is equal to negative omega naught squared, and then multiplied all times z, which is A cosine omega naught t plus B sine of omega naught t. And so we'll see here that if we distribute our omega naught squared through this, or it's our negative omega naught squared through this right-hand side, that we do get the same solution. And so then this tells us that our assumption was good. This was a good assumption, so we can go ahead and solve now for these constants. So we're going to solve for A and B. And so to solve for A and B using our boundary conditions, when t is equal to 0, then z at time is equal to 0 is equal to A cosine of 0 plus B sine of 0. We know that sine 0 is 0. We know that cosine 0 is 1. So this tells us that A is equal to z at time 0. Other boundary condition, z dot at 0 is equal to negative A omega naught sine 0 plus B omega naught cosine 0. So cosine of 0 is 1, sine of 0 is 0, and so then we get from this that B is equal to z dot at time 0 divided by omega naught. So now we convert back to our original coordinates. So remember, xm of t we said is equal to z of t plus x naught is our conversion. And then we also have x dot m as a function of t is equal to z dot as a function of t. So we plug all this back in. So we get x as a function of t is equal to A cosine omega naught t plus B sine omega naught t plus x naught, and then x dot as a function of t is equal to z dot as a function of t, which is negative A omega naught sine omega naught t plus B omega naught cosine omega naught t. All right, so, and this is where A is equal to z at time 0, and that's equal to x sub m at time 0 minus x naught, and also that b is equal to z dot at time 0 divided by omega naught, and that's equal to x dot at time 0 divided by omega naught. Alright, so then when we plug all this back in, go off the screen so we can see this. When we plug all this back in, for our constants, we'll get xm as a function of t is equal to xm at time 0 minus x naught cosine of omega naught t plus xm dot at time 0 divided by omega naught sine of omega naught t plus x naught. So here's our solution for the position, and then our solution for the speed is x dot m as a function of time is equal to negative initial position minus x naught unstretched spring length omega naught sine omega naught t plus our initial speed divided by omega naught multiplied times omega naught cosine of omega naught t. We can see here that our omega naughts cancel, and so that makes the last term x dot m, our initial speed, multiplied times cosine of omega naught t. So there are two state equations for this. Remember, this is a simple spring, it's a simple harmonic motion, oscillating back and forth, and there's no damping. And this solution that we see here is you really see this a whole lot, that's why this tutorial was called the ubiquitous spring, is because you're going to see this form in quite a few places. You'll see it in AC circuits, you'll see it in these springs, you'll see it in controls when you take that course. So take a look at the next tutorial before class. That's tutorial 2.4, and that's damped simple harmonic motion. We'll go over that tomorrow. And in addition, you do have a couple questions on your quiz that come from that tutorial. I'll see you in class.